In this lecture, we are going to discuss and apply unit load method, which is used to determine deflection and slope in a determinate structure. So the question here says that determine the deflection at point C in frame using the unit load method. So we have to determine deflection at this point. They haven't mentioned in the question whether we have to find deflection in the horizontal direction at C point or in the vertical direction. So it means that we have to find a deflection in both the directions. So in the case of unit load method, for calculation of deflection, we use this formula, and this formula of unit load is based on the principle of virtual work done, which says that external virtual work done is equal to internal virtual work done. On the left hand side we have the external virtual work done, and on the right hand side we have the internal virtual work done. This one over here is the imaginary or virtual unit load, and this is the deflection that we are interested in finding out. And inside the integral, the small m is the moment associated, moment equation for the member in virtual system. And the capital moment is the moment equation in the real system, moment equation of the member in the real system. So what is the difference between the two systems, virtual system and the real system? So this over here is the real system, in which the actual loads are applied. And in the case of virtual system, what we do is we take the same structure and remove the actual loads, that is this UDL and this point load, and then we apply a unit load. If I want to find deflection in the horizontal direction, I'm going to apply unit load in the lateral direction. And on the other hand, if I want to determine deflection in the vertical direction, I need to apply a unit load in vertical direction. These systems are the virtual systems, where you apply a unit load to them. You remove all the actual loads and apply a unit load at a certain point where you want to find the deflection. So if you want to find a deflection in lateral direction, you just need to apply a unit load in lateral direction. And on the other hand, if you want to determine deflection in vertical direction, just remove all the loads and apply a unit load in the vertical direction. So let's try to apply this formula to calculate a horizontal deflection. So if I just multiply something with 1, it's going to remain the same. And on the right hand side, this integral term is going to be written for each of the member. So in this case, how many members do we have? We have 3 members, AD, DC and DB. So for AD member, it starts from 0 and ends at 4. So the lower limit is going to be 0 and the upper limit is going to be 4. And inside this will be small MAD and then capital MAD over EI into dx. Similarly, we are going to write this integral term for this DC as well as DB member. So for DC member, it becomes starts from 0 and ends at 1. And inside we have MDC and MDC over EI dx, plus for the last member DB, it starts at 0 and ends at 4. So this is going to be 0 and this is going to be 4, MDB into MDB over EI into dx. So in order to determine horizontal deflection, we just need to determine these moment equations for the virtual system and for the real system. So the only difference between the horizontal and vertical deflection is going to lie in this term, in these small m, So if I want to calculate horizontal deflection, I'm going to use this virtual system. I'm going to find out the moment equation for this virtual system for each of the member. And on the other hand, if I want to find out the vertical deflection at C point, I'm going to use this virtual system, find out moment equation of each member for this virtual system. Okay, let's dive into the calculation. Okay, let's dive into the calculation of delta at C. That is the horizontal deflection at point C, or the lateral deflection at this point. So first we are going to determine internal virtual moment. To do that, we are going to remove these loads and then apply a unit load at point C in lateral direction. It doesn't matter whether you apply it in rightward direction or leftward direction. In the end, if delta at C is coming out to be positive, then it's aligned with your point load. So for instance, if it's acting towards the right and delta at C is coming out to be positive in the end, then your deflection is also going to be in the rightward direction with respect to this point. After applying unit load at point C, calculate support reactions. So at A, we are going to have two reactions since it's spin, and this one's going to be RAX, and this one will be equal to RBY. To determine reactions, apply conditions of equilibrium. So the first condition is summation of f of x, summation of forces in the x direction. We are going to take rightward force as positive, then RAX is going to be negative, and this 1 kilonewton is going to be positive. And RAX from here is coming out to be equal to 1 kilonewton. And if I apply a summation of f of y and take upward forces as positive, then RAY, since it's going upward, this is going to be positive, and RBY is also going to be positive. And let's name this equation as equation number 1. And now let's apply a moment at point A, that is at this point, and take clockwise moment as positive. So these two forces, RAX, RAY, are not going to create any moment about this point because they don't have any perpendicular arm, whereas this 1 kilonewton is producing moment, and we know that moment is force under distance, so force into this perpendicular arm, this is 5, and this is going to be positive since it's creating clockwise moment. And this RBY is creating a counterclockwise moment about point A, so this is going to be negative, and it has a moment arm of 4 meter. And if you calculate RBY from here, is coming out to be equal to 1.25 kilonewton. And if I substitute this RBY into this equation number 1, equation number 1 implies that RAY plus 1.25 equals to 0. And RAY from here is coming out to be minus 1.25, which means that the direction of RAY assumed earlier is incorrect. So this should be going downward. So this is wrong. And RAY is coming out to be 1.25, and RBY is coming out to be 1.25 as well. Now let's draw the free body diagram of this frame. To draw the free body diagram of the frame, separate the member at this joint and then apply the reactions. After applying reactions, calculate internal force here as well as here and at this end of the member. To determine internal forces at this end of the member, just apply conditions of equilibrium. So first we are going to determine this shear force. So let's apply a summation of f of x to this member only, and let's take rightward forces as positive, and then if you write this minus 1, this one is going leftward, so this is going to be minus, and this v is going rightward, so that's why it's going to be positive. So if we calculate v from here, it's coming out to be equal to 1. So this is equal to 1. And now let's determine the axial force here. To determine axial force, apply second condition of equilibrium, that is summation of f of y equals to 0, and take upward force as positive, upgoing force as positive. And let's name this force as A. Since this A is pointing upward, it's going to be positive, so plus A, and this 1.25 is acting downward, so this is going to be negative. And if I calculate A from here, it's coming out to be 1.25. So this force is equal to 1.25. Now the last remaining internal force here is the moment. So let's assume the direction of moment as like this and call it as m. Now let's apply summation of moment at D point, that is here, equal to 0, and take clockwise moment as positive. Now since this force is creating a counterclockwise moment, about this point, this is going to be positive, and it has a perpendicular arm of 4 meters. And we have this moment which is acting in counterclockwise direction, and this is going to be negative. So if I calculate moment from here, it's coming out to be equal to 4 kilonewton dash meter. So this m is equal to 4. Now let's try to calculate internal forces here. Let's first determine shear here. Let's name it as V. And if I apply summation of f of x equals to 0 to this segment only, then we have V is going left, so this is going to be negative, and this is going right, 1 kilonewton. So this is going to be positive. And from here, V is coming out to be equal to 1. And we don't have any vertical force, so axial force in this case, in this member, is going to be 0. And let's try to find out moment. And let's assume the direction of the moment as clockwise. And let's name this moment as m. To calculate moment, apply the condition of equilibrium at this point. That is, summation of moment at D point is equal to 0, and take clockwise moment as positive. This force is creating moment over point D in clockwise direction, so this is going to be 1 multiplied by perpendicular distances 1 meter, and this is creating clockwise, so hence positive. And this moment, that is the moment that we assumed, is acting in counterclockwise direction, so this is going to be negative, and m from here is coming out to be equal to 1 kilonewton meter. So m is equal to 1 and V is also equal to 1. Now we are going to determine internal force at this end of the member. To determine internal force, we are going to apply condition of equilibrium to this whole joint, D joint. So let's say first we want to determine this shear in this member. So let's apply condition of equilibrium again. Let's sum up the forces in y direction and take upward force as positive, and we have this V which is going up and it's going to be positive, and this 1.25 is also going up, and we don't have any force here, so this is going to be 0. And if we calculate V from here, it's coming out to be minus 1.25. The negative sign here indicates that the direction of force that we assumed is incorrect. This should be going downward. Now let's try to calculate moment here. To calculate this m, apply condition of equilibrium to this whole joint and take clockwise moment as positive. So how many moment do we have here? We have this m acting in clockwise direction, so this is going to be positive, and this 4 kilonewton meter moment which is acting in counterclockwise direction, this is going to be negative. and we have this one acting in counterclockwise direction. This is going to be negative as well. So if I calculate moment from here, it's coming out to be 5 kilonewton meter. So this is equal to 5. And now we need to determine this force. To find this force, apply condition of equilibrium, summation of f of x equals 0, and take rightward force as positive. So at this joint, at this end we have this v which is going left. This is going to be negative. And at this end of the member we have this one force acting in horizontal direction. This is going to be positive. And let's name this force as A. And this is acting in leftward direction, so this is going to be negative. So if we calculate A from here, it's coming out to be 0. After drawing the freebird diagram of the frame for this virtual system and calculating internal forces at each end of the member, we are going to write moment equation for this virtual system. So before writing moment equation, let's fix up our local axis for each member. So for this member, I've taken x in vertical direction and y in horizontal. And for this member, I've taken x here and y in this direction. And for this member, let's take x here. X is starting from this point and y going upward as positive. When I write equations, I usually move from left to right. So I start from here and go here. So when I move from left to right, I take upward shear force as positive and clockwise moment as positive. To write the moment equation, stand on the section C on the left hand side. Take the algebraic sum of all the moments. So how many forces are there which are creating moment about this section? Before this section, there is this 1 kilonewton force which is creating moment. So MAD is equal to, this force is creating clockwise moment, and since clockwise moment is positive, this is going to be positive 1 multiplied by x. Now we are going to write the moment equation for this member. Cut a section here, name it as x, and then stand on this section C on the left hand side. Take the algebraic sum of all the moments. So MDC is equal to, this force is creating clockwise moment. So this is going to be positive, and it has a perpendicular arm. This force has a perpendicular arm with respect to this section equal to x. And we have this moment which is acting in counterclockwise direction. So this is going to be negative. Similarly, write the moment equation for this DB member. Take this coordinate, this length as x. Use the same principle, stand on the section C on the left hand side. Take the algebraic sum of all the moments. So MDB is equal to, this moment is positive since it's clockwise, plus 5, and this force 1.25 is creating a counterclockwise moment above this section, and it has a perpendicular arm of x. So this moment is going to be negative 1.25 into x. And these are the moment equation for virtual system. Now the second step is to find M, capital M, which is the moment equation for each of the member for a real system. So this system is the real system because actual loads or real loads are applied to a frame. To start off, calculate support reactions. So first apply summation of f of x, taking rightward force as positive. We have this UDL going towards right. So first calculate the resultant point load by calculating the area of this UDL. The area of this UDL is 3 multiplied by 4, which gives us 12 kilonewton. And this is going to the right, so this is going to be positive. And we have this 10 kilonewton force which is also going towards the right, so this is also going to be positive, and this RAX is going towards left. This is going to be negative. If I calculate RAX from here, it's coming out to be equal to 22 kilonewton. And now let's apply summation of f of y, summing the forces in y direction. So we have two forces which are acting in y direction, RAY and this RBY. So RAY and RBY are both going to be positive. And let's name this equation as equation A. Now apply the last condition of equilibrium related to moment. Take clockwise moment as positive and take moment about this point, A point, and sum it equals to 0. So how many forces are there which are creating moment? We have this 12 kilonewton force, 10 kip, and this RBY. 12 has a perpendicular arm of 2 meter, and this is going to be positive since it's acting in clockwise direction, and this 10 kilonewton force is also acting in clockwise direction and has a perpendicular arm of 5 meter, and RBY has a distance of 4 meter and it's acting in counterclockwise direction, so this is going to be negative RBY into 4 equals 0. If I solve this equation, RBY is coming out to be equal to 18.5, and if I substitute this value into equation number A implies that RAY is equal to minus 18.5, which means that the direction of the RAY reaction assumed earlier is incorrect, and this should go downward, 18.5, and this is also equal to 18.5, and RAX was coming out to be equal to 22. So now let's draw the free body diagram. After determining reactions, draw the free body diagram of the frame and apply reactions to it. So this was equal to 18.5. We calculated these values in the previous step, and this was equal to 22, and at B the reaction was equal to 18.5 as well. Now we are going to determine internal force here. So first let's determine shear. So the shear can be determined by applying summation of f of x equals to 0 and taking rightward force as positive. This V is going towards the right, so this is positive. This UDL 3 kilonewton per meter is also acting in rightward direction, so this is also going to be positive, and it has a magnitude of, resultant point load has a magnitude of 12 kilonewton, so plus 12. And we have this 22 kilonewton force which is going towards the left. This is going to be negative, and if I calculate shear from here, it's coming out to be equal to 10 kilonewton. Now let's determine whether there is an axial force here. So apply summation of f of y equals to 0, taking upward force as positive. Remember, these conditions are I forgot to mention it earlier that we are applying conditions of equilibrium individually to each segment of the frame. First we are going to apply conditions of equilibrium here to determine internal force here. Then we are going to apply conditions of equilibrium here to determine force here. Similarly for this one. So apply summation of f of y. Let's call this force as A. This is going upward, this is going to be positive, and this is going downward. Minus 18.5 equal to 0. So A is coming out to be equal to 18.5 kilonewton. Now to determine this moment, internal force here, just apply summation of moment at this point, D point equal to 0, and take clockwise moment as positive. Then we have this 22 kilonewton force which is creating clockwise moment, and it's going to be positive, and with respect to this point, this has a distance of 4 meter. And then we have this 12 kilonewton force which is creating counterclockwise moment. This is going to be negative, and it has a perpendicular arm of 2 meter. And after that we have this moment M which is acting in counterclockwise direction, and this is going to be negative. So if I calculate moment from here, it's coming out to be equal to 64 kilonewton meter. Using the same procedure, calculate internal force here. To determine internal force here, just apply condition of equilibrium at D joint. So let's do that. Let's denote this force by V. Okay. And then apply summation of force in Y direction and take upward force as positive to this joint D, whole joint. So how many forces are acting in Y direction? We have this 18.5. We don't have any vertical force here, and this V. So 18.5 plus V is equal to 0, and V is coming out to be minus 18.5. And this negative sign indicates that the direction of this force assumed is incorrect. It should be pointed downwards. And this is equal to 18.5. Similarly, for moment, let's take moment as clockwise positive at this section and apply summation of moment at D joint. Take clockwise moment as positive. This M is acting in clockwise direction. And we have this moment 64 at this point, which is acting in counterclockwise direction. So this is going to be negative. And here we have 10 kilonewton dash meter moment, which is acting in counterclockwise direction as well. So this is going to be negative. So the moment here is coming out to be equal to 64 plus 10, which is equal to 74 kilonewton meter. Now to find the last remaining axial force here, internal force, let's name it as A, and then apply summation of f of x equal to 0 and take rightward force as positive for this joint. And we have this A going towards the left. This is going to be negative, and 10 kilonewton is also going to be negative, and we have this 10 which is going towards the right. This is going to be positive. And if I solve it, A is coming out to be equal to 0. So there will be no axial force here. So let's just remove it. Okay, now to write the moment equation for this real system. First, let me write down my sign convention. Upward shear force is positive, clockwise moment is positive. I usually go from left to right, so I take the sign convention as positive. And let's write the equation for this member. Let's cut a section here at a distance x, coordinate x, and M, capital M, AD, because it's associated with the real system. So that's why it's capital. And MAD, to write the equation of MAD, we just stand on the section, see on the left hand side, take the algebraic sum of all the moments. So there are two forces which are creating moment. This 22, which has a perpendicular arm of x with respect to this distance, with respect to this section. So this is equal to 22 into x, and this is going to be positive since clockwise moment is positive. And this UDL, and in this case the resultant point load for this UDL is equal to the area of the portion before this section. So this is equal to 3 multiplied by x. So this is 3 into x, and it has a perpendicular arm of x by 2 with respect to this section. So this is creating, this UDL is creating, 3x is creating counterclockwise moment. So this is going to be negative 3x into x by 2. Now let's write the moment equation for this member. Cut an arbitrary section. Let's denote this coordinate as x, an equation of MDC is written using the same principle. Stand on the section C on the left hand side. Take the algebraic sum of all the moments before this section. And for the last one, let's cut a section again and take this coordinate as x. And MDB is equal to this 74 moment is acting in clockwise direction, so this is going to be positive. And we have this force which is creating a counterclockwise effect about this section. So this is going to be negative. It has a perpendicular arm of x. Okay, I have listed the values found earlier in tabular form. This is the limit of each member, which is basically associated with length. For instance, AD member starts from 0 and ends at 4, and this DC member starts from 0 and ends at 1. Similarly, DB member starts from 0 and ends at 4, and we have this M real system and moment equation for virtual system. We found these values earlier, and now let's apply this formula to calculate delta HC. So delta HC is equal to integral. This integral is basically associated with AD member. So the limit for AD member, it starts from 0 and ends at 4. And we have this small m. The small m for AD member is equal to 1x. And the capital M for AD member is 22x minus 3 by 2 x square over EI into dx. Now let's write integral for this member, DC member. So this becomes 0 is the lower limit and upper limit is 1, and small m is equal to 1x minus x, and capital M is equal to 10x minus 10 over EI into dx. And we have this last member. Now write the integral term for this member. This starts from 0 and ends at 4, and we have small m equals to minus 1.25 x plus 5, and capital M equals to minus 18.5 x plus 74 over EI into dx. Now sum of these integral values using a calculator. So it's coming out to be equal to 870 over EI, and the unit is going to be kilonewton dash meter cube. So, okay, why is the unit of deflection equals to kilonewton dash meter cube? This should be something related to length, that is meter, because we haven't inserted the values of E and I here. If we had inserted the values of E and I, this would have been in meter. Also, we can derive unit from this formula. Furthermore, this delta HC is equal to plus 870 over EI. So this deflection is going to be in the direction of this unit load. We applied unit load towards the right. So this deflection with respect to point C is going towards the right, will be towards the right. So this is equal to 870 over EI. Similarly, to find vertical deflection at point C, that is delta HV, we are going to use the same procedure and method that we discussed earlier. The only difference will be in the virtual system, that instead of applying load in horizontal direction, we need to apply 1 kilonewton in vertical direction. So this will be our virtual system. And now we have to find moment equation related to this system. the vertical deflection at point C is coming out to be equal to 0. And also observe that this term on the right hand side is the virtual strain energy due to bending. It means that it does not incorporate or take into consideration shear or axial effects. And also in the question, if you see, they haven't asked us to include the effects of shear and axial for deformation. So that's why we didn't include any shear or axial effects. So delta VC is coming out to be 0 and delta HC was equal to 870 over EI. And we are done.